Hello, my name is Caleb and I'm a PhD student at Princeton University. Today I'll be talking about my work on optimization and analysis of ethanol production with carbon capture and sequestration. This is a type of BECCS which combines bioenergy production, which mitigates emissions from fossil fuels, with carbon capture at a biorefinery. And this allows BECCS systems to potentially achieve net negative emissions to offset industries that are difficult to decarbonize. I'll begin with an outline of an ethanol biorefinery. We take a feedstock and pre-treat it to enable access to the sugars. And these sugar ligamers are hydrolyzed into sugar monomers, which are fermented and purified into our product ethanol. The remaining sugars undergo anaerobic digestion and wastewater treatment to produce biogas, which along with the solids, mostly lignin, are combusted to produce heat and electricity. If the heat and electricity produced can meet the energy demands of the biorefinery, it's considered energetically self-sufficient, and any excess electricity can be sold to the grid. Ethanol biorefineries are interesting for studying carbon capture because there are three different sources from which carbon could be captured. There's the CO2 produced from fermentation, CO2 in biogas, and the CO2 in flue gas. This figure shows the relative carbon flows that we could capture from each of these sources. The most simple case is to capture no carbon, in which case we emit all of the CO2 produced to the atmosphere. We could capture from fermentation. We could capture from fermentation and biogas. We could also add on flue gas to those. What makes this complicated is that these relative flows of these streams is dependent on the biomass feedstock as well as the pretreatment method that we use. And previous studies and literature fix the facility. They fix the feedstock, the pretreatment method, typically the capacity, and predetermine from what streams carbon will be captured. And especially when they fix capture from all sources, that may require energy purchase. And that means that the refinery is no longer energetically self-sufficient, and emissions are incurred from the grid electricity that has to be purchased. So we want to understand the interplays between all of these variables. We use superstructure optimization. And in this, each block is described by a conversion coefficient, a unit energy requirement, and a unit cost. And that cost is further divided into variable costs, which scale linearly with the inlet flow rate to the block, and fixed costs, which scale sublinearly with the flow rate. And we use this superstructure optimization model to minimize the cost of ethanol production. We will examine how the cost optimal biorefinery design, as well as its energetic and environmental performance, depends on the feedstock used, the pretreatment method, the capacity of the biorefinery, and the level of carbon incentive that we apply. I'll talk through some of the specific configurations of carbon capture that I'll be referencing throughout the rest of my presentation. Like I said, the most basic case is that all CO2 produced at the biorefinery is vented to the atmosphere, and I call this configuration A. Configuration B, we capture just the CO2 from fermentation because it's very easy to capture and sequester. Configuration C adds capture from the CO2 in biogas, and configuration D adds on top of that some capture of flue gas, but only a small amount so that electricity is still being sold to the grid. Configuration E is when we capture exactly enough from flue gas to neither purchase nor sell electricity. And this is the most carbon that can be captured at an energetically self-sufficient biorefinery. In configuration F, we allow the purchase of electricity, and then configuration F is then the most carbon that we can capture. So In terms of results, I'll start by just showing what happens when we vary the pretreatment method and the level of carbon incentive. So we fix the biomass feedstock and the capacity. As we increase the sequestration credit, at first nothing happens for a given pretreatment because we aren't capturing any carbon yet, until we transition to configuration B, which is capture from fermentation. And as the credit increases, we eventually go to configuration C, which is capture from fermentation and biogas. When we get to flue gas, it depends on whether or not we allow electricity to be purchased. If we do, then the optimal is configuration F from here. If we do not and we require energetic self-sufficiency, then configuration E is selected. You'll see that in some cases, the level of carbon incentive required to incentivize capture from a given source varies widely between the pretreatments. For example, capturing from biogas, these three pretreatment methods have a similar cost of capture from biogas, whereas these two are much higher. And that's because these two, AHP and EA, produce very small amounts of biogas. And that sublinear scaling of fixed costs means that when more carbon is emitted from a given source, the cheaper it is to capture per unit of CO2. Over here, we show what percentage of the feedstock carbon can be captured. If energy purchase is allowed, some pretreatment methods can allow capturing up to half of the feedstock carbon. That's drastically reduced when energetic self-sufficiency is enforced, though less for some pretreatments because they have more excess energy available at the biorefinery. A commonly studied pretreatment method is dilute acid, in blue here, which reduces a lot of CO2 from fermentation and biogas, so it has a low cost of capture, but it has very little excess energy, which means that only a very small amount of CO2 and flue gas can be captured at energetic self-sufficiency. Looking at feedstocks, here I fix dilute acid pretreatment as the method because that's been the most extensively studied and still fixing the capacity. I consider three different feedstocks: poplar, switchgrass, and corn stover. Now, poplar and switchgrass sequester carbon underground as they grow, which is why their overall greenhouse gas balance is lower. Poplar is also more energy dense, so it can capture more carbon when energetic self-sufficiency is enforced. The cost of capture is higher because it produces less biogas, but the additional energy allows for both lower costs of ethanol production and up to just over a third of all of the feedstock carbon being capturable at energetic self-sufficiency. Now, in order to make this large scale, we need to have very large biorefinery, and that involves transporting biomass from far away. And the supply chain contributes heavily to the feedstock cost. For a small biorefinery, the easiest way to transport the biomass is to directly truck it from the harvesting site to the biorefinery. But as the biorefinery gets bigger and bigger, and the biomass is transported from farther and farther away, that becomes prohibitively expensive. And that's why we can use processing depots, which densify the biomass to make transportation beyond them cheaper, but they do incur their own costs. And after the depot, we can transport via either truck or rail, which have their own costs associated. This all comes together to have the optimal transportation method change as the distance from the biorefinery increases. The exact distances at which the cost optimal transportation method changes is dependent on the feedstock as well as on the local area. But this is the general trend. And this becomes important when we look at the costs of ethanol as we increase capacity. At low capacities, the ethanol is very expensive due to the high fixed costs. As we begin to increase the capacity, we have fixed cost savings because of that sublinear scaling. And eventually, we actually reach a minimum. And this minimum occurs because increasing capacity reduces the fixed costs, but it also increases the cost of the feedstock. So with no capture, for dilute acid and switchgrass, there's an optimal capacity of about 3,000 tons per day. When we add on capture from fermentation, the cost optimal capacity increases because there are more fixed costs at the biorefinery that we want to reduce. When capture from biogas is added, the optimal capacity increases drastically. And this is because we have a lot more equipment being added to capture from biogas. And it's now in this region of using depots and rails for transportation, which is a very low variable cost. And the cost optimal capacity increases even further when we add capture from flue gas. So you can see that depending on the level of carbon capture, we have a wide variety of cost optimal capacities that we see. Important consideration is the energy balance. We don't want to be consuming more energy to produce ethanol than there is energy in the ethanol that we're producing. Without carbon capture, the switchgrass biorefinery and supply chain consumes only about a quarter of the outlet energy in the ethanol. When we add carbon capture, that increases, but only up to about a third of all of the outlet energy when we enforce energetic self-sufficiency at the biorefinery. Concede that when we add capture from fermentation, we have only about a 1.5% consumption of our outlet energy, but a very big improvement in our greenhouse gas balance. And that's because that CO2 from fermentation is very pure, about 99% CO2 that only needs to be dehydrated before being compressed and sequestered underground. Whereas for biogas and flue gas, they require much more energy for less of an improvement in the greenhouse gas balance. And that brings us to obviously what is very important is the overall greenhouse gas balance of these large-scale systems. When we have no capture for ethanol production from switchgrass with dilute acid pretreatment, we are emitting carbon overall, about 23 to 26 grams of CO2 per megajoule. Now that is still much better than gasoline production at about 92. But in this case, as long as we have a high enough credit to incentivize capture from fermentation, regardless of the capacity, we are achieving net negative emissions. And as we add more capture, obviously the balance becomes better and better. And you can see that as we increase capacity with the same level of carbon capture, we do increase emissions, and that's because of the increased transportation distance. However, it's the increase in emissions slows drastically when we're at high capacities where we're using rail transportation, which has very low variable cost and greenhouse gas emissions. So I just want to conclude by saying that the feedstock and pretreatment method really impact how much carbon can be captured from these different streams and the cost of capture itself. And the amount of carbon capture that we use at a biorefinery can significantly impact the cost optimal biorefinery capacity. The exact optimal capacity will depend on the given location and biomass availability, but the level of carbon capture that is going to occur needs to be included when designing the scale of the biorefinery. And also the credits of only about $35 US per ton of CO2 are sufficient to incentivize capture from fermentation for all the biomass types and pretreatment methods that we study here. And for most of those, that is sufficient to achieve net negative emissions already with a credit this low. So that's all I have. I look forward to speaking with you further about this research. Thank you.